Hello and welcome to another video in our data science course. Let us begin today by talking about what we actually want to do in this chapter, because it's called How to Build a Model, and you might be inclined to think that we already covered all of that because we already know how to do a logistic or linear regression. So we might be tempted to think that we actually know what falls into the category of doing or building a model. So let's be more specific. What do we want to do in this video? We want to build a model that predicts the survival odds of the passengers of the Titanic, which is based on an infamous Kaggle competition. So here you see the Kaggle logo, which is a platform that is designed to bring together aspiring data scientists so that you can practice some data science on real-world data sets. And there are competitions, and one of the starting competitions when you register with Kaggle is that you get to work on the Titanic data set, which, as the name implies, contains information on passengers who have been on the Titanic when it sunk, and we have information on whether they actually survived or didn't. And the goal of that competition is to classify observations, so people, as either having survived or as not having survived. And fundamentally, this is what we want to do in this video too. And we want to do it because this will more or less show what more is included in this model building process, as opposed to simply just running a logistic regression. So let's begin by taking a look at the data set. And the data set is depicted here. I think it's just the first 10 rows of the data set. And here you can see that, for instance, there is a column or a variable passenger ID, which of course doesn't actually help us to do any forecasting or any classification, because this passenger ID is just something. It's just a number to classify the rows here or the observation. So this is not intrinsically something we can use for prediction, and this is something we need to take into account when we want to build a model. We cannot simply say, okay, do a logistic regression on all of that data, and we'll inevitably use the passenger ID column, which is nonsensical. Also, for instance, if you look at the variable age, then you will see here there are a lot of missing values, and we need to deal with those because often model specifications like linear regression or logistic regression, they don't work really nicely with missing values, so we need to figure stuff out how to deal with that. And yeah, these are two things we need to take into account before we can even begin to apply our logistic regression or whatever. In this case, we want to actually do a logistic regression because we're working on classification here, and logistic regression is more or less everything we know so far, or we learned so far, and this is why we will do a logistic regression here. And we see here now that we have to do some sort of pre-processing the data before we can begin to apply our model specification, our logistic regression. And yeah, this is also part of the model building process. Actually, it could be quite a tough part and can take up a lot of time. So we need to make sure that we are equipped to handle the common tasks. But before we can actually begin to do it, we need to think about one more thing, or a new concept, which is overfitting and underfitting. Basically, the idea is that you can match a data, or you can construct a model specification, like for the linear model, or just find just any equation that matches the data you're looking at too closely, or on the opposite, it doesn't match it very well. And this is what we refer to as overfitting or underfitting. For instance, take a look at our cars data set from our linear regression chapter, where we've in the linear regression chapter, we've fitted a linear model that kind of goes straight through here. So it does not go through all the data points. But you could think about just taking a data set and then drawing a line through each data point, and then you would have a model. This new blue line here would correspond to your new model. And of course, if you look at this data set only, your model would be really, really great because it matches your data perfectly. I mean, if you have this blue line and then you later check, okay, what is the distance it took me to stop when I was driving 20 miles per hour, you will just check the blue line and then you will get to the data point you actually had before. So that is a perfect match. And fundamentally, this would look like a great model then if you only look at this at the original data set. But of course, this model has no predictive power on any data it hasn't seen before, and this is why actually it is a bad model, but we don't see it if we only look at the original data. So in the overfitting scenario, this is what we refer to as overfitting. It matches the data way too closely, and on the opposite here I've just drawn a horizontal line, which of course matches the data not very well, which is of course, or perhaps more obviously, a very bad model as well. And as we can see here, this line is really wiggly, it has a lot of variance in it, but the great thing about this was that it matches the data perfectly, so there is no bias with respect to the data points. On the other hand, here we have no variance in the model. It's just a horizontal line, nothing happening, so no variation, but we have a huge bias because the data points actually look different than what we see there. And this is one of the big concepts in data science. It's the bias-variance trade-off. You try to minimize the bias and the variance, but you cannot minimize both. And this is why you kind of have to find a trade-off. And if you go to lean to one side of this trade-off, then you're going into overfitting territory, and leaning to the other side, you're going into underfitting territory. And what you want to do is find the sweet spot, basically, which is a perfect balance. And in the linear regression model, we did this, or we tried to do this by not matching the data perfectly via drawing a line that goes somewhat through the data but doesn't still match it perfectly. But still there's a danger of overfitting with this kind of stuff. And one method, or perhaps the main method to try to avoid overfitting, is to fit your model on one data set and then test the model performance on a different data set. This way you try to avoid this potential of overfitting, because you're using different data to evaluate your model than you used when you trained before. So instead, for instance, of taking all of this data set to fit a linear model that goes through some of the points, you just take a couple of points and use all the other points then later on for prediction, and see how close your model predicts the values it hasn't seen before. And this is the idea of using training data and testing data. But one very important thing you have to keep in mind is that you can implicitly still get overfitting into this, or an overfitting problem with this, if you use the testing data multiple times. For instance, in this scenario we just had, you could just take a couple of points for fitting the model and then check the performance on the testing data. And then you see, okay, the result is not that great. Let's try to shift my model a bit so that it later on matches the testing data perfectly. Then again, you will have the same problem of overfitting, because you have implicitly tuned your model to be a very good match to the testing data, but this might also mean that it's that you do something like this here again, and you will have something that has no predictive power on unseen data. So this is why you really need to, or you can only use the testing data once, and that is for your final evaluation. And if you want to check your model performance, you will have to do it some other way, or with some other data set, and we'll talk about how to do it in a second. But the really key thing here is that the testing data is only used once to evaluate your final model. Okay, so we got that covered. So again, this is something we will. This is something which is part of the model building process. You need to split the data. So by now we have seen we need to do some pre-processing to fill missing values, or to ignore some variables that have only IDs. And now we've seen we actually need to split data in order to avoid overfitting. And one key framework that helps us to do a lot of these common tasks that are part of the model building procedure is given by the tidymodels package, which is again same as the tidyverse package. Not really one package, but multiple packages. And here you can see that if you load library tidymodels, it will attach a whole bunch of packages. Some of them we have seen before, which is the yardstick package, which was helpful to evaluate classification. And we have seen infer when we were testing hypotheses. And there are a lot more packages, and we'll deal with a couple of them in this video. And we'll start by looking at our sample, which helps us to split the data. So how does it do it? We simply we take our initial data set, which I've saved in the Titanic variable, and then we use the function initial split. Ignore the argument here of this initial split function. I will explain it in a second. But this will split the data into training and testing data, or also sometimes referred to as analysis set and assessment sets. So this is why you have these names here, and you see that our complete data set of 890 observations was split into something 660 observations and 220 observations. So it's a 75-25% split, which is just the default, and which are common values. And so here you can see you don't actually get two data frames or two tables. You get something which is some form of object that contains all of the information. So everything is kept together, which is not really obvious why at this point why it's a good thing that everything is kept together, but that is maybe the tricky part about the tidymodels framework in the beginning. Things are sort of done in a convoluted way, and it's not really obvious why it is implemented the way it is. But for now, just rest assured that it's in this case it is helpful. And here you might wonder, okay, why do we even need to do something like initial split? We know the slice functions from the tidyverse, and the thing about this is that the sampling or the splitting the data is actually not as simple as you would think, because you have to consider a lot of stuff. For instance, you cannot simply take the first 600 rows and then the following 200 rows of our data set and then just split it like that, because what you want at the end is two data sets that are fairly representative of the original data set. And that means that if, for instance, the data set were sorted in the sense that the first rows are all filled with only people that didn't survive, and then come the people that actually survived. Of course, if you then split in the way I just explained, then you would have in the training data a lot of people that I forgot the order in which I said survived or didn't. In any case, if you split this way, and then in the training data you might have people that have only people that actually survived, and in the testing data you will have people that only didn't survive. And of course, this is a discrepancy, and training the model, like the logistic regression, would potentially then underestimate or overestimate the chances of survival, simply because in the training data there were not enough observations with respect to one of the groups. And this is why you need to sample properly, or to split the data properly. And another thing which we also did here is stratified sampling, which means that you actually need to think about, or again, need to make sure that your training and testing data are somewhat representative of the original data set, or so of the whole data set. And more specifically, you want to make sure that in both data sets there's approximately the same quota of survivors and non-survivors in the training and testing data compared to the original data set. And this is why, even though it sounds simple, splitting is sometimes not really obvious, and this is why the R-sample package really takes a lot of tasks, or does a lot of tasks for us, so that we don't actually need to think about this. And again, this comes at the cost of having something a bit convoluted here. So this is the output of this initial split. And if we actually want to get the tables that contain only the training data or the testing data, we actually need to apply a function to this split object. So in this case, we simply apply the training or testing functions. And now in the Titanic train, there is the training data set, so a tibble, and in the Titanic test variable, there's now the testing data. So again, a tibble. Another way to split the data is to use, is based on k-fold, or also called v-fold cross-validation, which is also something which the R-sample package can do for us. So it can do v-fold cross-validation. Again, this is just some stratified sampling to make sure that there are the same percentage of survivors and non-survivors in all data sets, or in this case in all folds. And what this does is that it takes the whole data set and doesn't split it in two. It takes a data set and splits it in here in 10. And this way we can actually use always 9 of those 10 sets to train our model, and then test our model performance on the remaining split we still have. And then we can iterate this remaining data set, so that it's not always the same. And this way we can iterate, can fit our model on 10 different data sets, which is the combination of always 9 of the 10 folds, or 9 of the 10 data sets, and then use the remaining one to test the data. So this is what we see here. It's not always exactly the same amount of numbers, but it's approximately the same. So here we always have approximately 600 training observations, and then we have approximately 67 testing observations. And all of that comes from the training data. So here we have used cross-validation to split our training data even further. Again, this is because the testing data is only supposed to be used once at the very end. But if I want to evaluate my model in between, I need to do some training and testing and then training again and so on. I need to iterate through that. And this is where these cross-validation folds come in. So each pair of training and testing is called a fold. This is what I'm always referring to when I'm saying a fold. We can use these multiple times, and once we find a model that is great with respect to these folds, then we can say, okay, now I'm using the whole training data to fit this final model, or to fit this final model, and then use the testing data to evaluate my final performance. Okay, so this is what cross-validation does. It splits the training data even further in order for us to somewhat evaluate our model in between, so that we're not basically driving blindfolded. So this is how this splitting part is handled. It's with the R-sample package. Another way to, or not another way, we're done with splitting, but the next thing we need to do is the pre-processing, right? I said this is one part of the model building procedure. I know procedure sounds like it's always the same step. It's just the things you need to do to build a model. So you need to do pre-processing, and all of that is done in so-called recipes. If you look at the tidymodels packages, you will see there is a package recipes. So from that package comes the function called recipes, which handles the pre-processing for us, or more appropriately gives us a framework for pre-processing. We still have to decide what we want to do with the data, but recipes gives us a framework to do it. Because think about these cross-validation folds. You will need to do the pre-processing for each fold, and so you will need to apply all of the pre-processing steps to each and every fold here, and therefore it would be great if you can collect all of your pre-processing steps in one function, so to speak, and then apply this function to each and every fold. This would be a great thing, and the recipe is exactly that. It collects all the pre-processing steps so that we can apply them to each fold separately and do not have to do some weird other thing in order to manage all of this pre-processing for each fold. And it also does a bit more for us. It also trains the pre-processing steps, because actually some pre-processing steps need to be trained. Think about the age variable in our data set. We've already seen that there are missing values, and we want to fill those values with something sensible. And the idea might be to use the mean or median age value that is given in our data. So this means we need to compute our median from the values that are not from the age values that are not missing, and this depends, of course, which data set I'm looking at. And therefore, you will always need to use the training data to train the median imputation step, so to calculate the median in order for it to fill the missing values with that specific median later on. And again, you will need to do this for each and every training data or analysis set in the folds, and then later apply it to the training data, the testing data. Because of course the testing data will only use the trained values or the trained median from the training data, which is maybe confusing in the beginning, but think about the scenario when you have only one observation you want to predict, then you couldn't compute the median from the testing data set. You need to have the median present already from the training data. And again, the recipe does all of that for us, and we don't really need to worry about how it does it, but still we should be aware that these kind of things are happening. And yeah, this is why I'm explaining it. So we're having the recipes for it, and the very basic recipe is basically stating what is our formula, what do we actually want to predict using what predictors, and what is the data. This is like the basic recipe which we have here. So the basic recipe is just what do we want to predict, giving what predictors is via a formula which we know by now. So here we want to use the survived, or we want to predict survived, the survived column, which just states whether someone actually survived or not. And we want to use all predictors in the data set to do that. And the data set is just the training data. And the first thing we could do in this recipe is just to denote that one of that column, the passenger ID column, is not actually a predictor, it's just an ID column. We don't actually need it for prediction, so we need to, in a recipe, we can simply update its role, and we do it by piping the recipe to this update role function, and the result of this computation is a recipe again, which now contains the basic recipe and the step we just added, which is just keep in mind that the passenger ID is not really a predictor. And with the same idea, we can do more pre-processing. So say in the cabin variable also has missing values, and we want to fill the missing values with missing, and all the other values will just be called available. Then we simply use step mutate as the next recipe step. And similarly, if we want to fill the missing age values with the median value from a data set, then we simply use step impute median more precisely. So this way we can handle all our pre-processing by filling our recipe with steps that need to be taken. And in this case, it's just step mutate to vary or to change the cabin variable, and here step impute to impute the age column. And this is how recipes work, and in the end, you after all these pipes, you have a recipe again. And if you look at it, the output will simply state, okay, what are the inputs? We have our new role here, ID, and here we see we have now 10 predictors instead of 11. And also it keeps track of all the operations we do. So technically this first step, this step mutate here, is not only filling missing values, it's actually changing the variable a bit, which is often referred to as feature engineering, so that you take the data and do some computations with it to come up with new variables or change the variable somehow. In this case, you could think about this cabin as actually being a new variable because it doesn't actually have the values from that are originally in the variable. It only has missing and available depending on if that data was missing or available. But in general, you can do even more feature engineering with recipes simply by taking the recipe we have done we have created so far and then chaining along a couple of steps again. And here in this particular case, I have computed a title from the name. So if you look at the data, you will see that the column name contains not only the name like James James Moran, it also contains like the title. So Mr., Mrs., can I find more in the first couple of rows? Sadly not. But there are more in there. But in any case, I can try to, from that name column, extract the title of it. And this could be a new variable I use for my classification. And this is what feature engineering is. So a feature is basically a variable or a column in a data set which you try to use for prediction. And in this case, I did some string matching here. You don't actually need to understand it. The point of this is it extracts the title from it, and then you will have stuff like Mr., Mrs., Miss. There's more. There's like master, there is colonel, there is doctor, and a lot of other weird titles people might have. And as you can imagine, it could be bothersome to have a lot of different levels in a categorical variable, which can be computationally expensive. And this is why you might want to stick to only the first couple of levels that are present the most, like Mr., Miss, Mrs., and Master. These are the 4 most common titles in the data set. And you can do it by using step other and apply it on this new title variable I just created using step mutate, and saying everything that falls below a threshold of 2%, so it appears less than 2% in the data, will just be classified as other instead of doctor, colonel, or whatever. And just to show you a couple of more steps, you could remove variables. I just removed ticket, the variables ticket and embarked. I don't want to use them in my analysis here. Of course, they could be helpful, but I just don't want to deal with those, so I just removed them. And again, I needed to update the role because the name itself or the name variable itself won't help me at all to do a classification. I already extracted what I possibly could get from that variable, but I might still keep it around for identification. So in the end, I will just assign it to the ID role again in order for it to be useful later on, maybe if there is some weird classification for a specific observation, I can then check the ID columns and see, okay, it's that person, let's see what's going on with that observation. This is why it might be helpful to drag along the ID variables. But again, the recipe makes sure that I know it's not really used for prediction. And then there are a couple of technical steps I need to include in my recipe in order for my logistic regression to work. Stuff like converting strings to factors, because categorical variables in R are usually dealt with as factors, and so we need to convert all of them. Or to, if you for instance look at the column P class, it's actually a categorical variable. It's just that the P class determines the class in which people were traveling, so first class, second class, or third class on the Titanic. And so this is actually a categorical variable, but it has numerical labels, and we need to make sure that that our model fitting procedure that knows that. So we also need to, for instance, convert this to a factor as well. And then there are more things. So these are the steps I just described. Then there's stuff like step novel. This is just a technical step that helps us to make sure that our computations don't crash. If, for instance, we have it in one of the folds, we have one training set that has a categorical variable that has only four different levels, but in the testing data there is another level that didn't appear in that specific variable. There's another level that didn't appear in the training data. Then my model would crash because the factor wouldn't know how to deal with that. And this is what step novel does. It makes sure that previously unseen levels are assigned to something. Usually it's called other. We can do this to all nominal predictors. We don't need to apply to a specific predicting variable, as opposed to here where we applied this step only to the P-class variable. Then we need to generate dummy variables, because as you know, linear regression, for instance, converts a categorical variable to a dummy variable, and this is a step we do with step dummy. Then step ZV is where the ZV stands for zero variance. If there is a variable that only contains one value, so that variable has basically zero variance, then we don't need it for prediction. It doesn't help us at all. So just to make sure we don't actually blow up the number of predictors we use, even though some of them have only one very specific value, throw them out. This is what step ZV does. And step normalize, make sure that all numerical predictors have zero mean and standard deviation 1, because that often helps to improve model performance. And these are a couple of technical steps we need to do for logistic regression. This is why I've added them here. For a different model specification like random forest, which we learn about next week, we actually need less steps. So the technical steps depend on what model specification we want. So in this case, logistic regression. And it's probably hard in the beginning to keep track of what we need to do, what technical steps we need to apply for what model. But luckily there is the use models package that actually generates a lot of template code, so that we can more or less copy and paste from that when we know, okay, we use the use models function to tell us what are the technical steps of or what are the steps for fitting a logistic regression. Then it will have like a recipe template, it will have a model specification template, and from there we actually could get these steps. Okay, so this is our final recipe. This is what we're going with. This is all the pre-processing we want to do. Let's apply this to data, right? We want to actually see how it works to pre-process a data set with this recipe. Well, as I said, first we need to prep something, so we need to train stuff like, for instance, training or computing the median, so we can impute it later on. This is what we would use in the training step. So this is why we need to prep a recipe. So we take this recipe and chain it to the prep function, which will prepare it. It will train all the pre-processing steps if they need to be trained, and then we can bake it and either on the original data set, so in this case the training data, so then you set new data equal to null, or you could actually apply these pre-processing steps to a new data set, and then you would have pre-processed the data set. So for instance, here you would see in this baked data set that there are new columns. So here it's title miss, title mister, title misses, title other. These are the dummy variables that were created from the categorical predictor title. And yeah, there shouldn't be any missing values anymore in age because we've imputed them. And so you see we have actually done our pre-processing in one simple chain. And technically we could now use the exact same thing to apply the recipe or the pre-processing to different folds. Okay, before we talk more about that, what are the next steps on our model building adventure? I owe you a dinosaur as always. So last week I made a transformation from one dinosaur with fork hands to two dinosaurs with fork hands, because obviously two dinosaurs are better than one. And for this week's picture, I decided to visualize this sentiment in a classical Drake meme, just to really stress that two dinosaurs really is better than one. So here is a classical Drake meme, and I just want to point out that this is actually all done in ggplot, or using ggplot, so it's not something I've done outside of R. So you can also include pictures into a plot. If this is really a useful way to use that functionality is debatable, but in any case it's possible. So there, enjoy the Drake meme, and once you're done with that, we can come back to finally the model specification, which I think I've been using that term throughout the video, but I haven't really talked about what I mean with specification, so I should elaborate. So the model specification is, or the word model specification is really just something I say in order to not say model again, because this word model is overloaded like a lot. You can say model to find a model to this whole procedure, so with this pre-processing and all that, but you can also use model to only mean that, okay, I use a logistic regression. And in the tidymodels framework, this language differentiation is handled by calling this method we apply, so like linear regression or logistic regression, by calling that model specification. And this is why I've used this all the time. That's our model specification, so we want to use a logistic regression. And this logistic regression function, or this logistic reg function, comes from the parsnip package, which is also part of the tidymodels meta package. And what this parsnip package basically does, it offers a framework to use multiple implementations of the same model. For instance, for logistic regressions, there are multiple ways to implement it in R. So we have only used the GLM function to use logistic regression, but there are others. And to unite all of those multiple engines, this is what a different implementation of the same underlying model specification is called in the parsnip package. To unite all of them within one framework, the parsnip package actually uses a logistic regression function, or uses this logistic rec function in order to specify a handful of parameters, for instance, and then saying, okay, I will use the engine GLM, for instance, in our case, and that way, if I had a parameter used in here, like, I don't know, I think penalty is one could use. You don't actually need to know what it means, but penalty is an argument that a logistic regression could use. But the point is, the penalty argument might be called in a GLM function, might not actually be called penalty, but I don't know, pen, whatever. I have really no idea what the true argument within the GLM function is, or if it can actually use it. I'm not 100% clear on that. But the point is, different engines, different implementations might use different argument names. And if you want to use a different engine, then you would have to rearrange all the argument names or whatever. And to avoid that, the Parsnip package actually gives you a unified framework that has a high-level function like logistic rec, where you can determine the parameters, and then if you throw that to set engine, it will handle all the conversion between the different argument names. That's the idea. And then, of course, some model specifications can be used for classification or regression. So you need to set the mode to either classification or regression. In our case, logistic regression can only do classification. So here it's a bit superfluous, but in general, some model specification can do both, and this is why the mode can be set. Okay, and this is actually all we need to do to set the model specification. It's as simple as these 3 lines of code, and then we can use the model specification for fitting and predicting, for instance. So we could use our pre-processed data, so our baked data set, and then we can throw our model specification, which we saved in Titanic spec, throw that to the fit function, and then say, okay, on which data are you supposed to fit? What is the formula? And then we can do a similar thing with predict. And notice here that we're not actually using the recipe here, we're using the baked data set. So this is why we need to restate the formula in here. And we need to make sure that the ID variables are not actually used for prediction, so we need to take them out manually. So this is how you apply the model specification manually, but it's not the most efficient way to do the fitting and training, for instance, for multiple folds and so on. But still, it's possible to do it this way, and this is why I'm showing you this. But what is actually more preferable, in my opinion, is to use another container that collects the recipe and the model specification into one, and that is given by a workflow, which comes from another tidymodels package called workflows, and it works similar to the other packages. You have like a empty workflow, same as you have a basic recipe, and then you throw that to different steps. In this case, you throw the workflow to add recipe, to add the recipe we defined earlier, and then we add the model in the same way. And now the workflow is like a container that collects everything into one. And as you can see here, it summarizes basically everything. It has a preprocessor, which is our recipe, and it has a model, which is our logistic regression here. And now we can use fit and predict again, but we don't actually have to remember what are ID variables and what is the formula, because all of that is saved in a recipe. So simply throw that to fit and then afterwards to predict, and then you can get predictions. And similarly, you can do the exact same thing for cross-validation. So remember, we have have 10 folds, and to apply this 10 times, this whole procedure is kind of tedious. So this is why there is actually a function which is called fit resamples, which can use these cross-validation folds. And simultaneously, it can also evaluate our model performance on these folds with respect to a certain metric. So for instance, for classification, we already know sensitivity or specificity. We could say, okay, train and test the model, the logistic regression, and all of that we have done so far on the different cross-validation folds. And then for each fold, check what is the model specificity, what is the sensitivity, and then later on I can I get a better picture of how do the sensitivity and specificity vary with respect to different samples we got from our data, so with respect to different folds, and I can combine these 10 estimates of sensitivity and specificity into one by averaging them, and then I have a more complete picture of a model performance, and I could evaluate then am I satisfied with this model performance, and I could then say yeah, then I'm all done, or I could say no, then I will have to tweak my model, maybe come up with some more features from the data, and this way I can actually do multiple runs of training and predicting, and then tweaking the model without running into the problem of overfitting. So all of that is done for us in the function fit resamples. We don't actually need to do all of this evaluation on our own. We simply take the workflow and pass it to the fit resamples function. It needs the Titanic folds or the cross-validation folds, of course, to so that it knows what to apply the recipe and the model specification to. It will need the metrics it's supposed to evaluate. You can give that with the metric sets, with a metric set you know from the yardstick package. So this is where the yardstick package actually help us. And then you could, for instance, use the control argument of the fit resamples function to say, okay, also save the predictions for me. If you don't say use that, then it won't save the predictions of the folds, because often we don't really need them, but sometimes it might be helpful. So this is a way to control for that. And yeah, again, this is where you see how the tidymodels framework is in the beginning a bit convoluted, because you interact with your data and the models with all sorts of functions. So here you simply want something as simple as, I also want to keep the predictions. All of that is handled through the control argument with this control resamples function, and here you could put in stuff like save predictions, and there are way more arguments, but it's convoluted. You don't have like a save prediction option simply in fit resamples. You need the control argument and the control resamples function for that. And similarly, the output is a bit messy. It has a lot of list-like columns in its output. It generates a table with list-like columns, and yeah, still we don't really immediately have what we want. We need to interact with this new data set, or this table we get, fits I call it. I could access this column manually. So here's where my metrics are in. The notes column is useful if, for instance, there are errors in the fitting procedure or whatever. This is where they will be displayed. As you can see here, all of the notes are empty, so everything went fine. And here are the predictions. So again, it's a bit convoluted. I need to work with this table through some helper functions. And in this case, I could, for instance, collect the predictions, which give us a better output. With which I can immediately see what is the predicted class, what is actually the true class, and also I can collect the metrics, and then I could say, okay, the F measure is 0.859. Am I satisfied with that or not? Depending on if I'm actually satisfied, I can then move on accordingly. So yeah, this has been the tidymodels framework. So we have already covered what is logistic regression, so that part isn't new. I wanted to show you how you use this maybe at first intimidating tidymodels framework, because it has a lot of moving parts in it. And I hope I managed to give you a good overview and a good summary and you see now how it works and maybe a bit of why the parts interact with each other the way they do. In any case, this tidymodels framework is fairly new, and so this is why things can always change in there. So there might be a lot of functions or names that could change. That's just part of an evolving programming language. But in any case, it's fairly new. It might be hard to learn in the beginning because there's not as much material for learning. And so this is why I want to take the chance to direct you to a great research with a resource for learning the tidymodels package, or in general how to work with it So I just want to recommend Julia Silgi's blog. So Julia Silgi is a software developer at our studio, and she's doing a lot of these screencasts where she's showing how to use the tidymodels framework for, I don't know, predicting stuff from different data sets. And she's using a lot of different functions from the tidymodels. She's using a lot of different model specifications, and you can find all of that on her blog. And basically, to be honest, this is how I got a good overview of the tidymodels framework as well, and I got to understand it better. So on her blog you will find a lot of entries. For instance, this one here apparently analyzes post offices in Hawaii, and you can always find her screencast for this specific model on YouTube, so on her video YouTube channel. And also you will always have the code here as well, so you can copy and paste stuff to figure out how you could maybe tweak the code in order to make it work for you. So yeah, that has been the tidymodels framework. I hope you got a good overview now, and I highly recommend, as I just said, Julia Silgi's videos. And yeah, that was our lecture, so see you next week. Bye.